Your phone is at 2%. You have a meeting in 4 minutes. You jam the charger in. You stare at it. It says 3%. This has been humanity's relationship with batteries since approximately forever. But in 2023, scientists built a working prototype of something called a quantum battery, a device that stores energy using quantum physics instead of chemistry. And the early results showed charging speeds more than 100 times faster than a classical device the same size. Scientists were, understandably, quietly losing their minds. To understand why that's remarkable, let's talk about how hilariously boring regular batteries are. A battery is basically a chemistry experiment you carry in your pocket. You have two electrodes, an anode and a cathode, separated by a material called an electrolyte. When you discharge the battery, lithium ions shuffle from one side to the other. When you charge it, they shuffle back. It is, in essence, a very small, very committed game of musical chairs. We have been improving this chemistry for 30 years. And the result is your phone charger, which says fast charging and still takes 45 minutes. That's it. That's fast. Fast compared to 1990. Not fast compared to, say, the laws of quantum mechanics, which we are about to meet. The problem is that chemistry has speed limits. Ions physically have to move through the electrolyte. There is a maximum rate. You can't just tell the lithium ions to go faster, they are doing their best. And no matter how many engineers work on the problem, no matter how many billions get invested, you cannot move a physical object faster than physics allows it to move. Chemistry is chemistry. It's not getting a software update. Quantum mechanics is the branch of physics that describes how matter behaves at the smallest scales. Electrons, photons, individual atoms, things that are so tiny they have stopped bothering with the rules that govern normal objects. At this scale, a particle can be in multiple states simultaneously. Objects affect each other instantaneously across distance, and particles regularly do things that are, in the technical sense, not supposed to be allowed. The property that quantum batteries exploit is called quantum coherence. When multiple quantum systems are coherent, they synchronize at the wave level, they stop acting like a bunch of individual particles and start acting like a single unified system. Think of it as the difference between a crowd of people all walking in random directions versus a marching band. Same number of people, completely different result. A quantum battery isn't one battery cell with quantum properties. It's an array of quantum two-level systems, tiny objects that can exist in either a charged or an uncharged quantum state. In the 2023 prototype, scientists used organic photovoltaic molecules trapped between two extremely close mirrors in a device called an optical microcavity. The whole thing was roughly the size of a pinhead. Inside, light and matter interact in a purely quantum way, storing energy not as chemical bonds, but as quantum excitations, as if each molecule is a tiny, perfectly calibrated spring. Now here is the part where it gets genuinely strange. In 2013, physicist Alan Bhattacharjee and colleagues published a paper proposing that quantum effects could dramatically accelerate battery charging, not just incrementally, but in a mathematically different category of speed. Their key insight involved something called the decay model, a description of how a group of quantum systems interacts with radiation, and their prediction was specific. In a quantum battery with n cells, charging speed scales as n squared, not n squared. To understand why that matters, double the number of quantum cells and you quadruple the charging speed. Add 10 times more cells and charging speed increases 100 times. Add 1,000 times more cells. You get the idea. There is no theoretical upper limit. This is not incremental improvement. This is a completely different relationship between size and speed, and it's the opposite of everything we know about engineering. Compare that to lithium-ion. Double the number of cells in a regular battery, and the charging speed stays flat, or gets slower, because there is simply more material for ions to travel through. The fundamental rule of battery engineering is, bigger means slower charging relative to capacity. That is just chemistry. Quantum batteries obey the opposite law. Bigger means faster. This is technically not how anything works. Quantum mechanics does not care. For about a decade after that 2013 paper, quantum batteries existed purely in theory. Great on paper, impossible to build. The problem is that quantum coherence is incredibly fragile. A quantum system that interacts with its environment, absorbs a stray photon, gets hit by a vibration, encounters anything at all, loses its quantum properties almost instantly. Physicists call this decoherence. The colloquial translation is, the universe keeps ruining everything, on purpose. The breakthrough came in 2022 and 2023, when multiple research groups figured out how to maintain coherence long enough to matter. The most significant result came from researchers at institutions including the University of Adelaide, working with organic photovoltaic molecules in optical microcavities. The key innovation: confine the molecules tightly enough between the mirrors that the vacuum fluctuations of light itself drive the quantum interactions before decoherence has time to kick in. The result: over 100 times the charging enhancement of a classical reference device at the same scale, 100 times faster. On a real device, in a laboratory. Not a simulation, a prototype. The team's paper described the result with the careful restraint of people who know that extraordinary claims require extraordinary evidence, and then quietly cited 15 papers proving they weren't hallucinating. Here is the detail that sounds like science fiction but is literally what is happening. The quantum battery charges faster specifically because the molecules are entangled with each other. The energy isn't deposited into each molecule one by one. The charging process acts on the entire collection simultaneously, as one quantum system. The energy doesn't flow in. It arrives everywhere at once, because everywhere at once is a valid physical state when you're operating at the quantum scale. Now, you're probably wondering about energy density. The 2023 prototype was tiny, nanoscale. It stored a very small amount of energy. And here I must deploy the most important phrase in science journalism: early results are promising, but the total energy stored was nowhere near enough to charge a phone. But the theoretical framework does not suggest any fundamental limit on energy density. The constraint right now is engineering, not physics. The engineering challenges are substantial. Maintaining coherence at room temperature for longer than nanoseconds is difficult. Scaling from a pinhead to a useful battery requires manufacturing quantum dot arrays at commercial precision. Integrating quantum storage with conventional electronics introduces new failure modes. When physicists say these are non-trivial problems, the translation is, we've identified the destination. We have absolutely no map for how to get there yet. Here is the twist in the story that most coverage misses entirely. The quantum advantage isn't just about charging speed. It's about how the advantage scales. Every battery technology ever invented gets worse as you make it bigger. More cells means more resistance, more heat, more inefficiency, more engineers quietly weeping. Quantum batteries are the first energy storage technology in history where scaling up gives you more advantage, not less. The bigger the quantum battery, the better the quantum effects work. It inverts the fundamental engineering problem. More cells means faster charging, not slower, for the first time, ever. This means the first practical quantum batteries will not be in your phone, they will be in grid-scale energy storage. Solar farms, data center backup systems, industrial applications where enormous amounts of energy need to charge in as short a time as possible. At large scale, the quantum advantage is largest. The technology makes physical sense there first, and then, gradually, the manufacturing gets cheaper and the devices get smaller. The realistic timeline goes something like this. Near term, quantum batteries stay in labs, being refined and scaled by a factor of 10, then 100, then 1,000. Medium term, roughly 15 to 20 years, grid-scale prototypes. Long term, in the optimistic scenario, commercial quantum batteries that make lithium-ion look like a toy from the 1990s, which it sort of is, but we don't usually say that out loud. So, in simple terms, scientists built a battery that uses quantum mechanics to charge faster than chemistry allows. The more cells you add, the faster it charges, which breaks every engineering rule ever written. It works in a lab. It's tiny. The hard part is scaling it up. But the physics says there's no fundamental ceiling on how fast a quantum battery can charge, which is either thrilling or deeply annoying, depending on how you feel about your current phone charger. That's quantum batteries. In simple terms, if this charged your brain cells faster than expected, the subscribe button is right there. Or don't. I'm a stickman physicist, not a motivational speaker.